Alright, so gonna look at FTC Centerstage initial robot concepts. So I've done this for the last few years for a couple games, and really enjoy doing it just to get some initial concepts together. So let's get into it. I really like this game so far. What have we got? So first impressions. It's similar to Relic Recovery, Skystone, and Rover Ruckus in 3 different scoring aspects, or scoring or design aspects. So with Relic Recovery, it's got the outside scoring, which comes back this year, except in the form of what did we say? It's the paper airplane, or the drone as they're calling it. And I really like that the scoring zone closest to the walls is worth the highest amount of points. That'll be an interesting challenge. I'm excited to see how teams are able to make the plane go there, because I don't know how you do it. I'm excited to see the different designs, or maybe design convergence. We'll see how it all works out. Return of the hang, so we're hanging again, as in Rover Ruckus, or what was the other game? Block Party. I think you could hang in Block Party too, which this hang is maybe more similar to Block Party than Rover Ruckus. It's also similar to Rover Ruckus in that the angled slides will probably be a big meta design to go on the back of the mosaic, because it's at a 30-degree angle, so you have an angled slide to reach up here, and maybe some people even have horizontal slides, but they'll drive over here and they'll reach out to cut down on driving time. And so that's a possibility. And then what else? We're going to have some new shooters this year, I expect, because we've never had to shoot anything like a paper airplane before in FTC, so that should be pretty cool. The first thing that came to mind for me was there's an ABU Robocon district tournament in Japan in 2022 that was focused on shooting paper airplanes, so I'll link the competition down there below if anyone wants to look at it. But there's a lot of really interesting designs that the students came up with for ABU Robocon. They do get to use more components, so like I know this one's pneumatic based, but there are a bunch of interesting motorized designs and some spring designs as well. So definitely a lot of inspiration to look at there. It's similar to Skystone, because this center structure in Skystone seems like more or less the same structure as this truss in Centerstage, so that's similar. So robots will likely end up being low profile, because it'll be a pain, I think, to have robots kind of taking turns to get through this, and so it's easier if you're just low to the ground, and so what is it, below 14 inches, just to squeak under it and get through. And then long sprints are going to be something I can foresee in this game, because it's a big open field. Unlike last year where there were all the poles, and so you couldn't really sprint super long distances easily. So it'll be interesting to see what drivetrain solutions teams come up with to combat defense and make those sprints as fast as possible. Alright, so going to look at 2 kind of very different robot designs in the rest of the video here. So one is going to be a pretty out there design that I just kind of came up with for fun. That's not maybe super practical, but I think it's cool, and maybe some interesting ideas there teams might take. And then the other one is a more conventional, a kind of lighter outline of a more conventional style FTC robot. And so, starting with the one that's kind of out there, this summer I competed in the Logic Coyote CAD competition, so it was an LCC, and I entered the robot, the Carnivore, which was a big extending robot, which we'll get into a little bit later. But that was the first thing I thought of when I saw this game initially. I was like, wow, so it looks like you might be able to have a robot that like sits right here and reaches all the way down to here and takes the pixels and puts them on the mosaic. And then I realized, no, you can't do that, because this is the blue zone, and if you were over here, you'd be scoring red and blue, and if you're here, you'd be scoring blue and red, which you don't want to do. But I really like the idea, so I'm like, so how could you make something like that work? Because the key benefit is it cuts down on the moving mass you have, so you can transport the pixels a lot faster. And so the adaptation I came up with is if you have a robot that is parked, say, right here, and then it has some sort of system that reaches up here, and then a horizontal extension that'll go, how did I put it? I think I put it like right here. And so the idea is you'd have a belt, a continuous belt, that would run all the way up here, so you could bring a pixel that is right here into your robot, and then you'd have another loop that would kind of bring it all the way up top here, and then have some sort of separate stacking type mechanism that would, and so this is playing the mosaic part like Tetris. So you would drop them down. So you'd have something that would sort them and drop them, sort them into the different possible locations you could put them in. And so the problem with this design is, how do you get your pixels if you're over here without going all the way into the zone, which means you'd have a really long extension, and then looking at the rules, that would be blocking because the Blue Alliance couldn't get to their zone. And so the solution I came up with was, if you have your alliance partner and maybe you cheesecake some sort of almost rake type mechanism onto their robot, which I think that's the FRC term for it, where you kind of give them a mechanism that it would just be like a little arm with a hook, and they might it flops down, and you can drag the pixels over into here, and maybe you could do it pretty quickly, and so that would narrow the distance that the actual a full robot, so your full mass of your robot, would have to travel, from going all the way from down here to up here, just from the the wing to the base of the conveyor. And so the conveyor could run really fast because all it has to do is run the pixels through it, and they're very light compared to a whole robot. And so you could run this at a comparatively low gear ratio and high speed, so you could move them faster than a robot could reasonably run them across the field, and it would suck it all the way up to the top into the scoring position. And so the double benefit of this is that, so now we're going to draw the Blue Alliance path. So looking at the rules, it's only blocking if it's obstructing all paths of travel to the object or area. And so maybe you'd move this a little more to this side, because I don't know if this counts as an area that's something you would, I guess if the robot can't fit through here, then yeah, it would be blocking, so maybe you'd have to move this over a little bit. It'd still be a shorter distance. But let's say you are able to move it because both robots can get under these here. Then it would be a bottleneck, because because I imagine you typically want to drive almost in a straight line across the field, because that's going to be your shortest distance. But this would force them to take a less direct route all the way through here. And say your alliance partner, the conveyor's alliance partner, was here transferring the pixel, then they would have to come all the way down and around here. And so not at all convenient. So it really limits their cycle time, because they have to drive a farther distance, because they can't do this one. They just have to do the two long ones. So I'm going to draw that again. So they could either do these two longer, I'll just draw a few of them, these two longer paths versus the shorter path. And so this slows them down and speeds you up, because you don't have to, or speeds red up and slows blue down because you don't have to move as much mass as far, so you can move stuff faster. So that's kind of the concept behind the conveyor robot. And so I'll sketch that one out over here then, based on kind of the robot I did for LCC. So LCC this year was a carnival themed game, and so you had to pick up this popcorn over here, and you had to transfer it into this big bucket. And so it was a similar field layout, where you couldn't just like park here and dump in here. And so you had to reach all the way down, it's not on the screen, but all the way down over here, and then drop them in here. And so this is a really, really long vertical extension that probably wouldn't work in real life, but was good enough for the CAD competition. It worked in CAD. And then here's the scissor linkage, which also I'm not totally sold would work in real life, as something that would move in and out quickly. So I was thinking, what if we just did this system, which, I mean, it would be pretty loose and maybe not very good as a vertical system, because it might just fall this way and droop because of the linkage, but it would work really well if you had something to brace it against, like the ground, for instance. And so that's the concept for the Centerstage conveyor robot, is that you would have some belt, as kind of illustrated in the drawing here, that would be on the ground, extended with a scissor linkage, and then you'd have some little intake system or intake roller here, and it would pull them through. And so that's the concept. So this, but on the ground, and then a separate system to score in the separate vertical system to score in the mosaic. I think that's what they're called. Let me double check. Oh, the backdrop, sorry. Not the mosaic. I've been saying mosaic the whole time. It's the backdrop. Still learning the terminology. So, let's see. Looking at the, well, I'll switch back and forth. So, let's do some initial drawing here. So I wanted to start at the intake end of the robot. So I'm just going to kind of sketch out a couple mechanisms here. So which one's the line? So this is the line tool. This is the first time I've ever used this software. So we'll see how it goes. Oh no, that's not the right not the right thing. Okay, so if this is our linkage, so it'll look something. We'll just have a repeating series of patterns, or a repeating series of links like this. And so this is inside the inside the end, and then let's bring this down to here. Okay, and so this is your initial linkage. So this is on the far side. So this would be on the field, the end closest to the. This is your intake side. Now let's use the pen or the pencil, and so you would have your belt, which would be secured to this point, and then it would run all the way back, and maybe you have a little idler here. You can't make those too big in diameter though, because then your linkage won't close up nicely. I think the linkage on the LCC robot, this whole thing, which it had some crazy distance, like it was more than 6 feet of extension, and it could pack up into like I want to say like 80 or 90 millimeters in thickness when fully retracted. So that's why you don't want to make these too big, because that increases that thickness when it's fully retracted. And so I'm just going to have this, because this goes all the way back. And so there's your conveyor. And maybe you use like a Brecoflex belt, which they're a company up in the northeast US, I think, that they make textured belts. We used some in a previous game, and so that would be your conveyor strategy, would be to have it kind of grippy. And then so this is just the conveyor belt. So how do you keep the I'll draw the pixel on here. I'll draw the pixel in, let's say, green. Well, no, because there's no green pixel. Let's draw the pixel in purple. So how do you keep the pixel on the belt? So you would have some sort of top and sides to constrain it in all the directions. And so what you could do is you could have some sort of textile. So that's the other thing with this belt. It'll come out and it'll tension itself because you're extending the linkage. And so when say this whole thing is loose, so say we have some sort of textile based, this is in the taut configuration, textile based top. If it were fully collapsed, it would actually like bunch up like this, if you can picture that. But when fully extended, it'll be straight, and so it gives something to press against. And you do the same thing with the sides, some sort of textile sides, because it's collapsible. And then, which I did on the chute, the vertical chute for the LCC robot. So this is, I mean, it looks solid, but it was supposed to be like a spandex type material, which would also put the thing under tension and put the linkage under tension, which might be good for holding its structure. And so then my thought was you maybe have some sort of little roller here, and so if this is the ground, oh yeah, so some little roller here, and then some larger larger linkage here, or not linkage but structure here, and maybe some sort of larger compliant wheel or something, and maybe this is belted or chained or geared or polycorded to this belt. So this roller, and this belt are all powered off the same motor back on the robot. And then maybe you have a, let's say there's a servo out here that would lift your thing up and down, which might help control the control intaking versus not intaking, and might help it fit better in size. And so that's kind of this concept out on this end, would be to have that as your intake. And so where's our purple again for the, yeah, so it would be like you'd pull your pixel and it would come all the way back. And so then if we go back into the robot, so this is like, imagine this is nice and long, so this is the end over here. And so then there's this whole distance, and then back on the robot side, let's see, what do we got over here? We got our belt coming in, which I think this is approximately the same color. I'm going to delete those lines. But yeah, so this is coming back, so, and then comes back into your robot. And so here's your pulley, you'd have a pulley, and then you'd have, what did I use? I used the pink for the linkage. And so this would be at this end, and then this would be right here. And you'd have your pins, which I forgot, but they rotate at that point. So this would be coaxial with the shaft that would drive this linkage out, which I'll show in CAD on the Conveyor robot. Kind of how that worked, which might make it a bit clearer. But you'd have a motor here, some drive motor for your belt, and you would run it to your conveyor belt. That's not exactly on center, but you get the point. We'd have some motor that would then run this whole system. The other thought I had was you could use a servo as a shifter and have some shifting mechanism, so that you could also use the same motor to run your linkage in and out, which would be convenient because then you would only need one motor right there, and you could package it conveniently. So you could use, I don't know, dog gears, or you could use, I don't know, a ball shifter seems kind of overkill, but you could use some shifting mechanism to switch back and forth between the linkage and the belt, because you'll want to contract this so you can hang in the end, and extend it in the beginning. So you want, and maybe run the belt backwards too in case it jams or something. So that's what you could do there. And then let's move down. So I bet I could maybe copy this. Let's see. Yeah, okay. So this is the inside the robot now. And we could have a intermediate belt that might be running off of this too, that would come back to here, and so that would suck your pixel in, and then the thought was you would have some mechanism that would, or kind of ramp that would transfer your pixel from being in this orientation to this orientation, where this is like a 30-degree angle, so you can score it flat against the other section. Oh no, that was the wrong tool. There we go. And so you'd have some sort of ramp and probably another roller as well, to keep it constrained. This is the, oh, I see what I'm doing wrong. Eraser tool. Keep it constrained against the backing and then you would have maybe some sort of roller that might be geared or somehow connected here, so that as it comes up, it's in constant contact with something that's moving. So this would spin. It's kind of hard to draw, but it would spin like that. So around that axis, and then that would bring it onto the next section of the robot, which would be the vertical kind of transfer up to the what do we call it? The backdrop. So that whole belt system is this, and then this transfer system is inside the robot, and that transfer system transfers it onto the part I'm about to draw. And so let's say we would have 2 sets of maybe 300 millimeter linear slides if we want to keep this in 14 inches in height. So yeah, no, I guess it'd be 3 or 4 stage to get to the necessary 35 inches in height you would want. And so these would be at an angle at the back. And I'm going to draw this. This is looking from the front of the robot. So this is looking at it as if we're looking at it back there. And so it'd be kind of off to the side maybe. But you would have it extended. So this is say fully extended. So I'm going to draw lines here to say that this is not to scale in length. And then you'd have another belt, another conveyor belt that would be tensioned by the extension of the slides. And so we'd have our 2 pulleys and our belt, and your ramp would lead up onto this from the front. So let's get that blue again. And so it's almost kind of like this, which it's hard to draw that perspective. And then I'll draw this pulley here, this intermediate pulley that's part of the transfer right here. And then our blue roller would be kind of like, I'm going to draw that maybe, I think this is the right blue. Yeah, this is the correct blue. Right here, and so that would help it. And so it spins along this axis, and that would help the pixel on its way up. And so the idea is your pixel would come in looking like this, and then it would come up this belt looking like, I'm just going to draw it as a square. Well, yeah, it's not a very good hexagon, but you get the idea. So that would bring it up here. So you rotate from in this plane to this plane, and it brings it up to your scoring actual like sorting mechanism. And so for that, I was thinking you would have some structure here that maybe would fold along this axis, and so it would fold down to be collapsed when you need to be in 18 by 18 by 14 inches. And then you would have some sort of servo up here. This is similar, if you look up, I think a bunch of rescue robots, a couple, maybe not a bunch, but a couple rescue robots had a mechanism like this, where they had some motor or servo, and then they had it's like a 3D printer axis, so it's like a belt along a linear slide, and then you would have a little finger here. And so, oh yeah, maybe this actually has to be farther back. Maybe back here, which imagine this whole thing's moved over. And then you would have your, against some backing here, you would have your pixel that's spit out into here. And then you would move it, and you could move it that way. So you can move it back and forth, and this is approximately the length, maybe not the full length, maybe this is like 15 or 16 inches across the whole backdrop here. So maybe you can't get all the way over here, but I don't think you're going to need to maybe necessarily do the whole thing. I've not physically seen a field, so I've not been able to play with that and see how they stack, but you'd have some distance that comes out, and maybe you have separate slots down here with each with a, so this is representing some sort of door, and then you'd have a bunch of tiny baby 9-gram servos. So like, you know, the little blue hobby servos or something that would actuate those, and so you would move it into this distance and then say, okay, I'm at this door. Maybe you'd have some laser distance sensor or something, or light sensor to detect when your pixel's in the correct position, and then you would drop it out the bottom, and so you could do that for all 3 of these positions or whatever. And so then that would fold up against there, and these slides would contract, and you'd be in your size. And then looking a little bit more at the CAD of how this contracts here. So this is the Conveyor robot for the LCC competition. And so I'm not going to contract the whole thing right now because it would take a really long time to load, but you can kind of see that you have a worm gear that drives this whole assembly, and then the other part of the linkage that keeps everything in line is actually the ground, because it has these little wheels. So I forgot to add that in the drawing, but you'd have to have little wheels, and so it folds up in there. Let's see if I have a picture of it collapsed. And here, yeah. So you could see it folds up kind of like that, and in this case it had to tilt. Maybe you would have to tilt it too, but that's exactly how it extends as it moves. When you push it against the ground, it moves out that way, so it's easy just to tilt it back more. And so that's kind of how that system works, to collapse that into size. And so that's a really complicated mechanism with a lot of things that can go wrong and a lot of things that need tensioned. I don't know, I thought it was an interesting design. As for drivetrain, I don't know, you'd probably just do standard Mecanum drive. For the meme, you could do 2 traction wheels and 2 Omni wheels and tank drive, because you wouldn't be driving a whole lot. Or maybe 4 traction wheels. There we go, even better. 4 traction wheels, just so you stay in place, and make it hard to drive. But so that's the complex design I kind of came up with. I thought was fun. And then let's see, what was the other design? So the other design is much more conventional. I'm just going to kind of very vaguely go over this one because I don't think it's as interesting, but probably. Oh, this would be the robot you would, the partner robot I was talking about here. This is the robot that you would have to cheesecake some sort of rake mechanism on so they can move it over into the conveyor belt. But I'll just draw it real quick down here. Let's do this. So you'd have your linear slides coming out the back at a 30-degree angle, and you maybe have some sort of motor or servo for pitch control, so you could move this back and forth. And then you'd have a standard drivetrain, Mecanum drivetrain, or locking Mecanum drivetrain, my favorite. But you would want it to be really fast. So that's the benefit of the new Go Builda wheels, is you can get really high acceleration because you would have larger diameter wheels. And that might be beneficial if you want to sprint all the way back here, and then you'd have some sort of almost oh, I forgot to make this comparison at the beginning of the video, but like Ultimate Goal, which was the Frisbee game, maybe a similar intake to an Ultimate Goal intake that would suck it into your robot, and then you'd have some sort of transfer in here, transfer mechanism, and then you would just back this up against the what is it? The backdrop. Back this up against the backdrop and drop it, and you could extend these slides. So if you didn't want to drop it all the way from the top, you could drop it in the middle, and that would be a much more straightforward and easy to build robot. And it would be faster to build, so you'd have plenty of time to program. I expect something like this to probably be the meta this year, maybe with horizontal slides in the front to reach out a little bit. But I don't know, just a guess. And another robot concept. So that's kind of all I had. If you have any questions, put them in the comments, or reach out to me on Discord. I think that's kind of all I got. Pretty cool game. Looking forward to what the teams come up with this year, and good luck.